all of you. So it's our pleasure to have Dr. Heidi Hamel today to speak to us about a very exciting topic, and I'm sure you have read a lot about it in the newspapers. So the subject is the James Webb Space Telescope. I can tell you that Dr. Hamel obtained her undergraduate degree at MIT. She's one of us. And then she went off to University of Hawaii to study astronomy and physics. Some of you may know that Hawaii has one of the strongest astronomy programs. And I didn't know until recently that there are 27 astronomical observatories in Hawaii. So it's the best place to train as an astronomer. And then after that, she went to Jet Propulsion Lab. She went back to MIT in the Earth and Planetary Science Department for almost 10 years. And then she worked on the Hubble telescope. And now she's working with the James Webb Telescope. So I won't read all her credentials because you can read it yourself on the NASA website. But I just want to point out, I just want to highlight the fact that not only she's an outstanding astronomer, she is a gifted communicator of science to the general public. She was in fact awarded the Carl Sagan Award for exactly that. So you're really in for a treat today because you're going to hear an exciting topic from somebody who can tell you, who can make the subject exciting. Now, as if that's not exciting enough, there's an additional excitement I want to tell you about, which is one of our own, Viguen Terminacion, who was one of my predecessors as president of the MIT Club, brought to us this show of an instrument that is now on board the James Webb Telescope. And this thing is called the Instrument Command and Data Handler. So that sounds like the central nervous system to me. So you are welcome to take a look afterwards. Unfortunately, we're not going to pass it around because it's kind of heavy. So please feel free to come up and take a look at it when the presentation is over. Okay, so without further ado, Heidi.
Thank you very much. So it is a pleasure to be here tonight with my MIT colleagues, alumni, guests, family. I really appreciate the opportunity to share with you some of the latest results from the James Webb Space Telescope. This is a program that I have been working on for over 20 years. Very, very long time commitment. My daughter here will tell you of the hours and hours I spent in telecons and meetings, traveling all over the world, working with the team to help build this telescope. My role is as an interdisciplinary scientist. I am one of 6 interdisciplinary scientists selected by NASA in 2002, 20 years ago, to help advise NASA on the science use cases and help with science decision-making for this telescope. So I'm going to start, because I am an educator at heart, and I know that not everyone here took 802. I'm going to start with a little bit of background in physics and some science to ground you in what you're going to see later, all right? You need to have some background to truly appreciate what you're going to see. So we'll start with Isaac Newton. Isaac Newton did an experiment where he put a prism in a little hole in the wall and spread light out into its constituent rainbow of colors. But what's important for us, James Webb Space Telescope, is that the spectrum of light does not end at red or stop at blue. The light continues on, in the case of the red end, with longer wavelengths of light, And in the case of blue, the wavelengths get shorter, but there is light there, although we cannot see it with our eyes. And you know the names of these kinds of light. You've heard of radio, you use microwave light to heat your food. Visible is what we see, ultraviolet is why we wear sunscreen. You know about X-rays because you get them when you break your toe like I did last night. And gamma rays is another high energy kind of photons. What's important for James Webb is this region, the near infrared and the mid infrared. Webb actually can see a little bit into visible light. For those of you who like angstroms, we start at 6,000 angstroms. We in our field tend to use microns because when we work in the infrared it's more convenient. 6,000 angstroms is 0.6 microns. And this telescope goes from 0.6 microns out to 28 microns. So another piece of information for you to know about light, infrared light, there's another word for it, and that is heat. Like we feel in the room, that is infrared radiation that we are all sharing with one another. And so from visible light to thermal infrared heat, that is what we're going to be working with James Webb Space Telescope. The universe emits light at all of these wavelengths. The universe does not just emit visible wavelengths of light. And so astronomers want to use all the wavelengths, all the way from radio dishes, all the way through to gamma rays, all right? And we do have facilities that do all of that work. And we have had some infrared telescopes in the past, but they have been very small telescopes, right? So Webb is not the first infrared telescope, but it is the most powerful infrared telescope that we've ever built. So I'm also going to talk about something called spectroscopy. And I want to show you a few slides about it, especially for those of you who did not take all the 8 courses. For you non-MIT people, that's all the physics courses at MIT. When we break light out into its constituent rainbow of colors, and remember, it doesn't end at red, it goes all the way out. It doesn't end at blue, it goes even further. But certain materials and molecules, they absorb light at specific wavelengths, depending on the physics of what's happening with those molecules, their temperature, their pressure, their dynamics. And so by looking at these patterns of absorbed light, you can learn stuff about things out there in the cosmos that you cannot touch or visit. And other materials emit light, right? They're under certain pressure, under certain conditions, you got a cold thing and a hot thing behind it, blah, 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 blah. I'm not going to go through all the details because most of us went to MIT already. We don't need to do it at dinner. So you could have extra light and missing light. And in the early days, when we were using light as a tool in astronomy, we didn't have rainbow printers. We had black and white printers. So we had a code for showing these things. And we took the background as a straight line, but when you added light, it went up. When you subtracted light, it went down. And this is called a spectrum. And NASA's official terminology for a spectrum is a squiggly line chart. And NASA hates it when we show squiggly line charts. They only want us to show pictures. But you cannot only show pictures. You must show spectra because that's where the science is. And let me give you an example. Here's a beautiful image from the Hubble Space Telescope of an exploding star called Eta Carina. And that's a Hubble image. But, and many of you have seen this, those of you who love astronomy. This is a classic exploding star. And Hubble actually did more than take just an image. It, in fact, took a spectrum of the exploding star. And here I have it going out, and you can see the lines here, and we can identify them. And what that tells us is inside this exploding star, you have helium, argon, iron, nickel, all of this chemical material. We can see that from the spectrum. You'll never see it in a picture, but the spectrum is where the science is. Okay, so spectrum equals science. It tells us composition. It tells us temperature. It tells us pressure. It tells us dynamics. It tells us so much about these things in outer space. This is the astronomer's primary tool. And so for JWST, I will be showing you spectra. So you needed to understand why. Okay, another very important thing about JWST is, why did we infrared telescope? Why didn't we just make it a bigger Hubble and have more pretty pictures to show everyone? There was a specific reason for that. And that specific reason is because the universe is expanding. And not only is it expanding, the expansion is accelerating. So the further you look in the cosmos, the most distant galaxies, those are moving away from us. And what that does is it shifts the light. It expands the wavelengths of light. Remember what happens in the spectrum? What happened when the wavelength got longer? Where did it move? The visible moved into the red. And then when we ran out of red, we went into the infrared. Okay. So a nearby star, here's a spectrum. Here are some hydrogen lines, these Balmer series lines. You can see them with their lovely labels, just alpha, beta, gamma, delta, epsilon. But if you look at a nearby galaxy, you still see those Balmer lines. But if you look closely, you see they're shifted just a smidge to the red. Maybe you can't see it. But if I take you to an even further galaxy, now you can see it, right? And if I take you to an extraordinarily, really distant galaxy, now look where they are. They're shifted way into the red. And so one of the key science tasks that astronomers identified even before Hubble was launched was that we wanted to see the first galaxies that ever formed in the cosmos. And what this tells you is that you can't do that in the visible. You must build a telescope that is sensitive to infrared light, because that's where these key transitions will be. And that is why JWST was built as an infrared telescope. That is the primary reason. Now, there's a ton of other science you can do with an infrared telescope, as I will show you, but that was the driving cause. That was the raison d'etre for this telescope, the first light machine, first galaxies. All right, so let me tell you something else. Well, this is the last bit of science I want to throw at you, because infrared light has other very interesting capabilities. Here's a picture of a guy holding a trash bag over his hand at visible wavelengths of light. Here's the same guy with the same trash bag with an infrared camera. Notice what you can see that was invisible to you at visible wavelengths. The infrared light penetrates through this garbage bag as if it's not even there, because it is sensing the heat from his hand. It's not sensing visible wavelength, it's sensing infrared wavelengths or heat, okay? The same thing is going to be true in astronomy. We have a dusty nebula, and when we look at it at visible wavelengths of light, we see dust, but when you look to the infrared, what we can see is right through the dust. So here's an example. Do you recognize that constellation, Skywatcher friends? Orion, okay. Did you know that Orion was actually just a tiny hole in a super large cluster of or nebula of gas and dust? When you look at Orion in the infrared, this is what you see. This is the Orion Nebula that you all who are Skywatchers know. It's this little smudgy thing right here. It's actually a hole in the nebula, all right? And this is the nebula. This is the gas and dust that's glowing warm. It's hot dust. You can see it in infrared, and you can see right into this little pocket where new stars are being born, all right? So this is with an infrared telescope on the ground, but what we're going to do is we're going to do this with a supergiant space telescope optimized for infrared. So this just gives you an idea of another aspect of infrared light. Okay, so why do we put this thing in space? Why not build it on the ground where it's a lot easier? You don't need giant rockets, et cetera, et cetera. There's three reasons. The first reason is, not that. It's not this. I don't know. Jennifer wants control of my screen. What? Should I say yes, Jennifer? Decline, decline. The room is saying decline. All right. Okay. Here we are. Back. We're back. All right. I won't push that button again. Okay. First reason, atmospheric absorption. That's what this chart shows you. It shows you the electromagnetic spectrum that I showed you and what reaches the ground and what does not, and what is absorbed by the atmosphere. So I don't care how big your telescope is. If you're looking at X-rays, you will not see them on the ground. You must be in outer space, all right? And that's true at radio. That's true here in the infrared too. Now we used to have a flying telescope. We used to because it's being decommissioned. But there's another thing that we have to worry about. So infrared does not reach the ground really. Some tiny windows it does, but overall it can't. So infrared, that's sending us to space. Atmospheric distortion, even in the most finest observatories like Mauna Kea, at the summit of this mountain, you still get distortion from the Earth's atmosphere. So that's another problem. But the third problem, the real super reason we had to go to space, is sensitivity. And how many of you are a little bit warm right now? Yeah, a lot of you, right? So if we put James Webb in this room right now and tried to measure infrared radiation from the cosmos, could we do it? No, because we would be swamped by the warmth of the people. And the same is true of the Earth and the moon and the sun. All of those things are sources of warmth, all right? So we have to put Webb far away from the Earth. It is not in low Earth orbit. It's very far away from the Earth so that we keep it super cold. All right, so that's why it's in space. So here are the two telescopes you hear a lot about. This is the Hubble Space Telescope. This is the James Webb Space Telescope. Notice a couple of things. First of all, notice there's no tube that encloses the telescope. Why is there no tube? What would the tube do? It would be warm. This tube here is made of stuff that would just get warm and radiate warmth. So we don't want it, all right? Same thing with these support structures. The reason they're super long and super skinny is to be as thin as possible. Another main difference, this giant sun shield, its very name tells you what it does. It shields this telescope from the sun and the Earth and the moon, not just visible light. Notice that there are layers here. These are layers of kapton. And every one of these layers reduces the warmth that hits this side and makes it a little cooler and then a little cooler, a little cooler. So by the time you get through 5 layers, you have dropped the temperature by over 600 degrees. So this telescope is 600 degrees colder than the ambient space, but it's still not cold enough. So we have what's called a cryo-cooler system on there. It's a thermal electric cooling system that is down on the warm side and snakes up here and basically has a kind of a circuitry system that pulls temperature out of the instruments so that our mid-infrared camera operates at close to 7 Kelvin. All right, so that's 7 degrees above absolute zero. That's the temperature you need to sense the warmth of the distant universe. All right, so those are the main differences. This is the mirror of Hubble. It's a 2.4 meter mirror. The Webb mirror is segmented, and its total effective area is 6.5 meters. So it's almost 3 times larger than Hubble. So it's a super fantastic, fabulous telescope. And why is it coated in gold? We didn't choose that because it's cool looking or because it's expensive and we want to charge the federal government a lot of money. We picked gold as the coating because gold is an extremely efficient infrared reflective surface. So this is the surface that we need to reflect infrared radiation, not aluminum or other kind of coatings that we have for visible wavelength radiation. The total amount of gold covering all of those mirrors is about the size of a golf ball. It's just spread out across 6.5 meters. Okay. Let me talk a little bit about our instruments. This is half a scientific audience. So some of our instruments do imaging. Some of our instruments do spectroscopy. You will notice that we have a lot more spectroscopic modes. Why is that? Science, for the science, that's right. There is good science with the imaging too, but for the astronomers, a lot of the real meat is in the spectroscopy. So there's so much spectroscopy being done. Here's wavelengths in microns. And over here is our visible B, V, and R. You can see these are 4,000 to 6,000 angstroms. So this is what your eyes can see. And you can see that we're picking up just in the very red here with some of our instruments. A near infrared camera, a mid infrared camera, another near infrared, I can't remember what near stands for in the moment. It's another kind of imaging system. The near infrared spectrograph, this was a contribution from the European Space Agency. They built this. And MIRI, again, is also spectroscopic. NIRIS is an instrument built by the Canadian Space Agency. So this is a fully international project. And we will be using all of these things. For those of you who remember some of your physics, we do have aperture masking interferometer on board. We now use integral field units for all of our, for imaging spectrograph systems, single slit spectroscopy, multi-object spectroscopy this is an amazing new device that the NIRSpec is using. It's an array of tiny apertures. By tiny, I mean, if you imagine a penny, you have several dozen apertures inside just that penny. And so we can open individual apertures to do different spectroscopy on a crowded star field. So it's a really incredible, fabulous system that the Europeans built for NIRSpec. Okay, so the science that we plan to do. You can't read it. Those of us in the room can't read it, but what it says is first light and the first galaxies. That's the key driving science goal for this telescope. But it is so powerful that we selected a science team, including myself, to do other science as well. And so the next science case is the assembly of galaxies over space and time. So watching the evolution of galaxies from the very beginning to the modern day. Also, examining the births of stars and protoplanetary systems, stars that are surrounded by disks that someday may host planets. How do stars get born? How do they die? That's all part of this science theme. And then finally, the science theme that I have been a part of for 20 years, planetary systems and the origins of life. And this includes our planetary system, the solar system. And that was, in fact, my proposal to NASA. I will use this fabulous tool designed to see the first light in the universe, and I'm going to use it to look at Neptune and Jupiter and asteroids and comets and Mars. And, they bought it. They selected me. So when you see any planetary stuff coming out of JWST, that's mostly coming out of my program. Okay, so Merry Christmas. Last Christmas, December 25th, I was at the Space Telescope Science Institute because we launched JWST. So we're going to try to play a video, and apologies if those of you on line can't hear it. It's a rocket launching, so you can make the rocket launch sounds in your head. Okay. This is in French Guiana at the European Spaceport. That's why it's in French. It only launched one rocket. We'll just see 5 or 6 views of it. Same rocket. It's an Ariane 5, one of the largest European rockets.
Decollage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Look at this lady. This was me.
Through the clouds, 20 seconds into the flight.
So scary to spend 20 years building something and putting it and lighting the fuse.
Ariane 5 rocket continues to
Solid
fly
rocket
up the
boosters
orbital
are separating. It's off the ground. A lot of us were crying. Okay. Now I'm going to show you a video that we actually didn't expect to get. Those of us who had been working in the program for a long time kept saying, you have got to put a camera on this. We want to see the telescope unfolding. It was all folded up to fit inside there. And we were told, no, that's impossible. You can't do it. We didn't know this, but the Ariane company actually put a little camera inside their rocket fairing. So we were able to see the telescope drifting away after it separated. Let's see if we can make it go. There we go. So that's the back end. You can see the rockets firing. You see around the blue ring there. See the rockets going. Here's Earth. It's separating. It's moving away. And it was such a perfect launch that the solar panel array deployed while we could still see it. None of us expected that. It was actually designed to deploy about 5 or 6 minutes in, but it deployed within 2 minutes in because the launch trajectory of the Ariane 5 was so perfect that it put it exactly on the right path. And another important thing about that perfect orbital injection was that we did not need to use extra fuel to put it on the right orbit to get it where it was going. And so we now have an extra 10 years of fuel that we didn't know we were going to have. Now, our instruments may not last that long. Space is actually a rough environment, but if they do, we have the fuel. Okay, so it was launched from Earth. It then took a month to traverse out to the L2 point. As I said, it was folded up to fit inside the Ariane 5 fairing. There is no rocket large enough to hold the sun shield. That sun shield is the size of a tennis court. We just don't make rockets that big. So it was a very, very complex maneuver to unfold, spread it out, unfold the secondary. You can see this, the sequence here, and we couldn't see any of it. We had telemetry. We had information from the rocket saying something moved and I've released this bolt and something's happening and the mass distribution is changing. So we could track it, but we couldn't see it. But everything went according to plan and it fully deployed and went into orbit around the L2 point. What is the L2 point and why did we put it there? So if you took a line from the sun to the Earth and kept going 1.5 million kilometers, that point is called the L2 point. It's the Lagrange 2 gravitationally stable point. There are other gravitational points. There's L1, L2, L3, L4, L5, but we chose L2 for this because we put the telescope here and we actually, remember that sun shield? What we do, it doesn't look like this, it looks like that. That's the orientation of the telescope all the time. And it is always in an orbit around L2. And it is just following that line. And it's always looking out, in this case down, but it can look here, it can rotate and look up there. So we will never look back to Earth. We will never look at Venus. We will never look at Mercury. Everything beyond that is fair game, including some near-Earth asteroids. Okay, so we just are now in orbit around L2, and L2 is orbiting the Earth. We are now in 24/7 JWST operational mode. There's a Twitter feed. If you're on Twitter, called JWST operation, and it'll tell you every moment what JWST is looking at. So I follow it. Today it said, we're looking at Patroclus, and I wrote, woohoo! I mean, this is part of our program. It's an asteroid that a spacecraft is going to go to. So let's see. Once we got to L2, it was 6 months of commissioning the telescope, which is why you didn't hear about any results. And I'm not going to go through this incredibly complicated diagram. It's from a blog that I wrote about how we commissioned this telescope. So if you're interested, you can type into Google, why 6 months until science? And this blog will come up and it'll explain the whole thing to you. But it's basically taking remember it was a segmented mirror. Every one of those mirrors had to be aligned to work together as one mirror. So all 18 mirrors have to end up as one view. And it does, and it works, and it's fabulous. And, you know, we knew it would be, but you know how it is when you know it's going to work. You're just like, oh yeah, it's going to work. It's going to be great. These are smart engineers, right? But it did work. Okay, and so here's some images from NIRCam, the Fine Guidance Sensor, NIRIS, MIRI. These were images showing you that it was going to work, and it did work. And I wanted to show you, before I get to the science, this is like the last prep slide. It's a sequence of images from other infrared telescopes to show you why JWST was so special to us. The WISE telescope was a small telescope. Spitzer is another very famous space telescope, and it's better than WISE. But this is what JWST brings us. Do you see the difference? I hope you do. It's 20 years of my life, that's all. You know. But this is the difference of the progress in infrared astronomy over the last 20 years. And this is the apex. I mean, this is where we're at. So now let's talk about the science. This is really why you came. You didn't want to hear all the background, but you needed to understand what was going on. So let's talk about our very first deep field, all right? This is a deep field of a piece of sky called SMACS. We have lots of silly names for things in astronomy. What this is here, what you're seeing is a cluster of galaxies. These white smudgy things, each one of those white smudgy things is a galaxy that is composed of billions of stars. And there's a cluster of them here. And it's so much mass that this cluster bends space. That the mass bends space. And anything that's behind it gets refocused. So a very, very distant galaxy behind this cluster is refocused. And that's why you see these little streaks. And you notice that they make kind of a circular pattern. Are you seeing that? Do you see the circular pattern? That's mapping that out allows us to map out the mass of these galaxies. We can weigh a cluster of galaxies by looking at an image like this. And let's do a little tour here. Let's zoom in a little bit, just so you can see a little bit more some of these central galaxies. Now, when you zoom over off to the side, what you see here, everything you see that doesn't look like this is a galaxy. Billions of galaxies in the background. There are some foreground stars that you see, but it's just galaxies. Some of them are very young and very fresh, but some of them are extremely old. When you find little tiny red ones that look just like a dot, that's a distant, distant galaxy. And I think the one thing I want you to take away from this is that this was 12 hours of JWST time. The Hubble Deep Field that revolutionized astronomy, it took 10 days to make the Hubble Deep Field, the first one. And this was 12 hours. This is just a first look. Imagine what we are going to see when we do the true deep fields with James Webb Space Telescope. I mean, yeah, it's going to be amazing. So this was just the first look deep field here. All right, so let us, this was a Hubble image of the same field for comparison. So you get an idea. We did some frontier imaging of these clusters. And you can see everything is there, including that bright foreground star. But again, JWST takes us so much deeper. Yes, was Sure, yeah. The question is, why do the stars look like these crazy patterns? We call those diffraction spikes, and that is actually light diffracting around the three, remember holding up the secondary mirror? There were three things that were sticking out from the telescope. That's what gives you sort of a six-fold pattern. This 1, 2, 3, 4, 5, 6. And there's an extra one here that goes across the center that has to do with diffraction off of another edge in the optical path. Every telescope has a different diffraction pattern. What is special about JWST is we model this with fundamental physics, diffraction, and it is incredibly stable. And we have pictures of the planned diffraction pattern and compare them with the on-flight diffraction pattern. We are working at the edge of physics. There's no extraneous stuff. Everything is understood. So these are very stable. They never change. And so we can model them out when we need to. But in pictures like this, we leave them in because they look super pretty. Yeah. Okay, so let's move on to a little bit of science. Y'all remember we talked about spectroscopy. Here's an example where they picked out a couple of different galaxies in this field, and they were able to measure spectra of them. And look what you see. Remember when I showed you how close things were, the light was at 1, but when you went further, the light shifted, and when you went further, it shifted some more, and you went further, it shifted some more. Here it is in the data. This is not a cartoon. This is for real's data. And by picking out any random galaxy and measuring where the lines are, what do you learn? It's distance, right? And it's age. So from light, we learn distance, we learn age, and we learn chemistry as well. People have, once the data went online, the papers started flowing. These are two examples of competing papers, pulling out every little red thing in there and trying to measure its distance. Some of them are not right because it's instant science, but some of them are right. So one of these galaxies, what we call a glass Z13, is probably, it's been confirmed by several groups now, it's probably formed only 300 million years after the Big Bang. So it's super young galaxy. All right, here's another example of chemistry from one of those galaxies where they spread out that light, and what you see in the galaxy is neon, hydrogen, oxygen. So even a galaxy that is like 30 million years old, we're still measuring the chemistry that's taking place here with James Webb Space Telescope. Okay, let's turn to the birth of stars. I'm sure you've seen this cosmic cliffs picture and have marveled over how beautiful it is. What is it, some of you may be wondering, aside from being just a pretty picture? What this is a dusty cloud here. And way up there, you can see the bottom of a spike of a bright star, right? The bottom of the diffraction spike. This is a place where hot young stars are being born. And as they're being born, they have violent winds that they blow out. And the violent winds blow into the dusty environment in which the stars were born and form hollows inside the dusty environment. So the blue up here is a clear area. And these are dusty environments. So what you see up here, this thing sticking up, at the top of that is a star that's being born. It's a high density star environment. And it's so high density that the wind is blowing against it, but is not eroding it like it is in the areas on either side. So you know inside there is a newborn star. And if you look closely, you can see things like that throughout. You see places like here, you can see some jets, and they're being blown out of that star. So this is a very, very rich image showing you a star formation area of the birth of a star. Interestingly, so yeah, I should have done that. I was zooming in to show you that thing. Forgot to use my own clicker. So you can see that. It's very beautiful. You go along the edge of this cliff. You can see other regions that are thicker like that. You know, there's stars in there. Like there's probably a star being born. Here's a very thick region of dust in there. And so it's just an incredibly rich environment to work with. So we also can take a piece of it and actually look at our long infrared wavelengths and look at what happens when you go to a long wavelength. Did you notice? Remember the trash can? How you look right through it? When you went to the longer infrared wavelength, you look right through the dust and you see all the stars being born. Like here's one of those clumps and you can see the stars inside there now. So that is a zoomed in version. And this one is especially spectacular, bursting right out of its natal shell. Okay, here's another image that just recently came out. This is a Tarantula Nebula. I think it came out 2 days ago. So you may not have seen this one if you're not following JWST on Twitter like I do. This again is another star formation region. In here is where all the stars are being born and they're blowing out the dust away from them. And you're able to just peek through this little window inside to this star formation region. And so I thought we could just zoom in just a little bit just to get a close look at some of these bright young stars, very hot young blue stars. Notice the difference in color of these hot young blue stars and this foreground star, which is an older, yellower star. So you can pick up information like that from images like this. Here's a picture of the end of a star's life. This is one of the original images that was shown. This is a Hubble image of something called the Southern Ring Nebula. And when you take the same Southern Ring Nebula with the infrared, the near infrared camera on James Webb Space Telescope, that is what you see. And what is happening here is there's a star here, and that star is dying. It's in the end stages of its life, and it's blowing off shells of material. And you're seeing the remnants of these shells all around you here. It's thinner in the middle, so you can see through the shell. Now, one of the big surprises here was actually that this star is not the star that is dying. And you only found that out when you went to the long wavelength, the mid-infrared images of JWST. If you zoom in and switch to the mid-infrared camera, look at that. That is the dying star, but it is enshrouded in this warm dust. You cannot see it at the near infrared wavelengths, but you can see it glowing in this far infrared wavelength. But it was invisible to Hubble, and it wasn't until you had JWST that you could see the actual star in the middle of this nebula. So that was a little bit of a surprise to a lot of people. It's kind of fun. Okay, planets around other stars. When we started planning JWST, we only knew of like 3 planets around other stars. We call them exoplanets. Today, 20 years later, we now know of over 5,000 planets around other stars. And JWST is going to be a fantastic tool for analyzing the light coming from planets around other stars. But like I said, when we started it, they were known to exist, but we had no targets for JWST. So the key way, there's sort of 2 ways of studying them. One is really hard. One is that you have a star and nearby is a planet and you take a picture of that planet. That's hard because stars are really bright and planets are not. That usually only works for really far away, super large, super Jupiter planets, right? For regular Jupiters and Neptunes and Earths, you don't have a prayer of taking a picture of the planet. You can't do it next to a bright star. We do have a thing called a coronagraph, which blocks out the bright star, but it's still really, really hard. The main workhorse tool for studying exoplanets is by a technique called transit spectroscopy. A transit is when your planet crosses in front of the star. And when it does that, it blocks out the starlight. But the starlight is refracting through the planet's atmosphere. And so at the bottom here, you get a signal from the atmosphere of the planet. And if you do it at different colors of light, you can actually figure out the chemistry of that atmosphere by looking at different colors as the sunlight shines through it. And so this transit spectroscopy is a really powerful tool for studying these things. So here's the first example of a transit spectrum that came. And what you see in this planet's atmosphere, this is a planet called WASP 96b. What you see here, all these bumps correspond to water in this planet's atmosphere. Gaseous water. We're not talking about liquid water. We're talking about gas, but they're very real. And the reason astronomers around the world were all overjoyed is that this is great signal to noise here. You know, there's nothing iffy about it. This is real detection of water. So this was a proof of concept for this, for JWST. And the teams are now working away at studying dozens and dozens of exoplanets. Here's a very cool paper that just came out very recently called The Identification of Carbon Dioxide in an Exoplanet Atmosphere. And it's doing exactly what I said before. All these are transits taking at different colors of light. And so by looking at the depths of these transit and all those colors, you can map out the spectrum. And what they found was carbon dioxide. This is a little video, which I hope I can make work, which kind of, for those of you who like this sort of thing, it sort of gives you a different visualization of what I've done there. It made sense to me, and maybe it'll make sense to you. I found it on Twitter. So I put the guy's tweet so that he gets full credit for it. Let me see if I can make it work. There we go. So he's showing you time on one axis, wavelength on the other axis, and he's zooming in to show you the difference in the depths of those different transit lines. And that difference in the depths is what we pull out as spectroscopy. So I just thought that was an interesting visualization of that plot there made by Everett Schlawin. So I thought that was neat. I liked it. It helped me understand that pretty well. And this is what they found. Now, remember I was talking about how great the signal to noise of the other one was? Well, look at this one. Carbon dioxide, hello. There's no question, absolutely solid detection. We're going to be doing this kind of work for dozens of exoplanets. And I will share with you that the JWST is probably not the tool that we're going to use to find life on an exoplanet. Because a lot of people want to know that. Well, why don't you look at another Earth and see if there's water and land? It's really hard to do. They have to be close enough that we can get the transits. They have to have the right orientation. That's a statistical thing, right? Because you have to have the orientation such. And there just are only about 5 or 6 potentially Earth-sized planets at a habitable zone distance from their host star. In other words, at the right distance that water could be liquid. There's only about 6 that we know right now. And believe me, we're going to be studying those 6. But to really do the job right, to answer the question, are we alone in our local galactic neighborhood, requires a much larger telescope than JWST. And you can ask me about that in the Q&A because I have an answer for you on that. Exploration of galaxies. This is a lovely collection of galaxies called Stephan's Quintet. 1, 2, 3, 4, 5. Number 5 here is actually a foreground galaxy. Do you notice it looks a little different than the other ones? It's not as fuzzy and smooth. That's because it's way, way closer to us, but it just happens to lie in the same field as the other 4. These 4 are together, and they are interacting galaxies. They are physically interacting with one another. So this is a picture using the near cam and the mid-infrared camera. We're going to zoom in a little bit on this one. You can see the beautiful structures up here. Those come from the infrared camera. Now this one, of course, you can see individual stars in this galaxy. So that'll be an interesting exploration. But when we go back to the distant ones, the stars are not visible. They're too far away. It all blends in together. And you can see in the in-between areas, things connecting them. Those are real. Those are real interactions of these galaxy groups. And again, off to the side, what do you see? More galaxies. Every image with JWST is a Hubble Deep Field, no matter what you're looking at, even Jupiter. So let's see. Now this is a purely infrared image of these. We've taken away the near infrared and only looking at the far infrared. You're looking at the hot bits there. All right. So in the places where there's these interacting flows, it's very hot. Star formation is going on. And in this galaxy, you can see sort of a spiral pattern-ish thing of star formation. When we combine it again, we can pull out spectra of the different regions. So here's a spectrum of the core of this upper galaxy in the quintet. And you see molecular hydrogen, silicates, neon, sulfur, oxygen, most of the usual suspects. They're there. Okay, this is, for those of you who care, we can also do dynamics. I think I'm not going to talk about this because I've been talking a lot, but it just gives you a sense of the depth of the science that we can do with these galaxies and with JWST. This is a cool image that Janice Lee, who's the chief scientist at Gemini, made. It's a single galaxy called NGC 7496, and she compares the blue is the Hubble image, and the red is the JWST image. And what you can see, JWST highlights the star formation in these spirals really beautifully. So it gives you a sense of what's dark in Hubble, these dark lanes, that's where stars are hot and being born. So I like that picture. And then there's our local neighborhood, the galaxy. This is all the science that I and my team are going to do. So far, we have only released one thing, and that's Jupiter, all right? But I will tell you today, I'm not going to give you any details, but I will tell you today, I got the first look at images of another planet in our solar system, and I was talking with my postdoc who works at Goddard, and so this is how it goes with JWST. She said, look at that stuff at the mid-latitude. It's like there's a hemispheric asymmetry. What does that mean? And I'm like, I don't know. We've never seen anything like that before. And she's like, oh, what about this thing down here? I'm like, it's brand new. This is, this is exploration at its finest. And so, yeah, so I'm really excited about that. But I'm not going to give you any details because I'm not allowed to. But it's very exciting. I hope I've communicated to you how interesting it was. It's like, I don't know, but I've never seen that before. This is the best image of X since Voyager. All right, so it's fun. All right, so I showed this one not because it's great data, but it shows you something that we worked on very hard. This is a little asteroid, and we're focusing on the asteroid, and these are stars. And we're showing you that we can track moving targets. And that was like 7 years of my life to make that happen. So I'm very happy about that. This little asteroid is called Tenzing. And it's named after one of the explorers, Norgay Tenzing, Sherpa, who did mountain climbing. Okay, so here is our image, Jupiter. And it's a lovely image. We worked very hard on it. I'm going to do a little tour of some of the new and interesting things that we found in this image of Jupiter that JWST is providing for this planet, even though we have sent multiple spacecraft and 2 orbiters to this planet. We're still learning things with JWST. Let's start up in the north. And it's still working. For those of you online, that was my computer falling off of the stage onto the floor. But it's still hooked up. Oh, no, now we got to plug it back in. No, it's just loose right here. You got to push this. Hold on. Okay, I think we're back. All right, is everybody ready? That was exciting. Thinking maybe I need to drink a little bit after that. All right, are you all ready to continue our tour of Jupiter? Okay. Do you see this red stuff up here? If you look really closely, you can see like some red lines on the planet. The red lines on the planet are the aurorae borealis of Jupiter. What this red stuff is new. It's showing us how high the aurorae are extending up above the cloud tops of Jupiter, which we did not know before. We have beautiful Hubble images of ultraviolet aurorae, but these infrared aurorae show us the vertical extent. So that's new. Let's zoom down to the southern hemisphere. And you can see, again, beautiful auroral emission. I wanted to show you this one. You see there's a little red dot if you look carefully there. That is not a cloud. That is the auroral footprint of the moon Io, which is sweeping up magnetic material in Jupiter's magnetic field. When it goes past Io, it picks up sulfur and other material from the volcanoes on Io, entrains it, and then dumps it in the atmosphere to make a visible spot. And let's take a look way over here. If you look carefully on the limb, it looks like there's an extra line there. When we first saw this image, you see there's like a shadow of the limb. And people are like, whoa, it looks like your image is not in focus there. We're like, yeah, the image is in focus. It totally is in focus. Well, what's that line? And we're like, well, I don't know. We've never seen anything like that before. And so there's a hot debate going on now in the astronomy, in the planetary astronomy community about what this is. Could it be a detached haze layer? A very high altitude haze layer that's high enough that it's reflecting light? Maybe. Or a friend of mine says, no, that's ionization. That's an ionization layer at a very high altitude. And you're picking up ionized molecules and seeing them up there. And the bottom line is that we actually haven't decided if it's one of those two theories or if it's something else altogether. We don't know yet because this was the first that we had seen that. Let's take a look at our old friend, the Great Red Spot. Why is it not red? You know the answer, because it's not a visible wavelength, right? So it's not going to be the colors you're used to. But why is it bright? Well, the answer is it's bright because there's a high altitude haze trapped in the top of this storm. And that haze is reflecting sunlight back to us before it can be absorbed by molecules in the surrounding atmosphere. So high things are bright. And that's why the Great Red Spot is so bright here. And I wanted to zoom out just a little bit because you'll notice there's a lot of other really bright things. They're kind of up there too, little bright streaks. Those are the tops of thunderclouds, convective storm cells that you can detect and pull out of these images. And we're going to be able to pull out a lot of good atmospheric science from the images of Jupiter like this. And so that's just a little short tour of just that one image. We also have a wide field view of this that is taken at less wavelengths, so not as colorful, but it shows some other very interesting things. If you look closely here, you can see a ring system. We knew it was there. Voyager discovered it, but it's extraordinarily difficult to image from Earth and from the ground because it is so faint. This ring is 1,000,000 times fainter than Jupiter. I hope that gives you a sense of the amazing dynamic range of James Webb Space Telescope. 1,000,000 times fainter next to this incredibly bright planet, we can image the ring. You can see a little tiny moon, Adrastea, another moon, Amalthea. This bright light here is a diffraction spike. Remember the diffraction spikes? Io, the moon Io is off to the side here, but its diffraction spike is visible here. And that's what that line is. You can see the aurorae. The aurorae have diffraction spikes as well, but they're extended. So they kind of make kind of a diffraction spike bar. I don't know what the right language is anymore, but you can see that in here as well. And I always like to end by putting things into a local context for you. Oop, all right, did it work? I lost my local context. But let me just talk about this then. No, it's what's coming. This is a cartoon that our team made up showing JWST and all the things in the solar system that we will be looking at. So I hope stay tuned for asteroid spectra, comet spectra, Mars images and some spectra, Neptune images and soon spectra, Kuiper Belt objects, including our friend Pluto, spectra, and so much more. If I didn't mention your favorite solar system object, maybe it's Titan. Yes, we will be looking. Saturn, yes, we will be looking. And we're just getting started. As I said, these were the things that we planned to do with JWST. What we learned with Hubble is that if you ask what is the most important stuff we've ever learned from Hubble Space Telescope, what's the best science, half of it we thought of when we were building it, but the other half was things we hadn't even imagined when we launched. And so I showed you today the things that we had planned to do with JWST, but so much more we haven't even thought of yet. It's going to be young scientists, who are kids, weren't even born 20 years ago when I started working on this project, but they will be doing some amazing science. Okay, so here was the local context. I forgot about that other slide. All right, so we're going to zoom in on Adrastea here, right? Now, Adrastea is a super tiny moon. We don't have much information about it, not even from Voyager. And how big is it? Oh, I hit the wrong button again. Sorry, my bad. Yeah. All right, how big is Adrastea? It's 20 by 16 by 14 kilometers across. So even with JWST, we're still only going to see a little dot like that. But I thought I'd put it in local context for all of us here, those of us who are here in Washington, D.C. Here it comes. All right, here we are at Busboys and Poets. Oh my God. Life is difficult. Here we are at Busboys and Poets in the middle of that. This oval is the size of Adrastea. All right, and that's what you just saw with JWST at Jupiter. So I'm trying to give you a physical scale, literally physical scale for how big things are. And remember though, that Adrastea is our local neighborhood, and we're going to be able to see things like galaxies out to the very edge of the cosmos and everything in between. JWST, I mean, we had amazing plans when we were building it. When Bigland was helping us to build the pieces of it, we had an idea and we had hope, but on orbit, it's even better than we had dreamed. Everything is working perfectly. The sensitivities are better than we had planned for. In some of our pictures, the images are saturated because the sensitivity is stronger than we expected with the cameras. So it is an amazing tool. I'm finishing with this image of this deep field that you saw. And I wanted to end with one last thought experiment. Remember I said that these arcs were distant galaxies that are being refocused by that cluster inside? If you look in this refocused image, you can start to pull out individual stars in that distant galaxy. And so we may, if we're lucky, actually be able to measure the light from some of the first stars that ever formed in our universe, from which these first galaxies were formed. It's a stretch goal, but this image, this first image from JWST suggests that we may be able to do that. And that is a first light machine indeed. So I hope that you have enjoyed hearing about Webb. We are in a new era of astronomy as of Christmas with this launch of this new telescope. Thank you all.
Okay, so we're going to take some questions from the live audience first. There are about 10 questions right now from the online audience. So we're going to take a few and then we switch to the online questions and then we come back here.
I'm sorry, you're doing,
No, why don't you?
okay, yes, sir.
Thank you. Incredible presentation. Incredible. A general question. Are we doing any the 3D database of all the locations of all these galaxies so that we model the universe and maybe kind of density of mass in the foreseeable future?
Okay, I think I understood your question, but if I didn't, correct me. You were asking if we're creating databases of all these galaxies. Every observation taken with JWST goes into an archive in Baltimore called MAST. It's called Mikulski Archive for Space Telescopes, named after Senator Mikulski. All data goes in there, and it is, most data are typically proprietary for 1 year, but then they become available to the entire world. So all data from Hubble ever taken is in the archive. Every image from JWST will be in the archive, and all of it is available to astronomers. And we have found with Hubble that nowadays papers from the archives are becoming just as important as papers by the original proposers. So that archival data is available to everybody. Am I getting at your question? Oh, the three-dimensional. Yeah. Oh, okay. So, yeah, we have not only the positional in the sky, but as you saw, by using the light, we can measure 3 dimensions. And so there are projects that are modeling the three-dimensional space of the universe. A telescope like Hubble or Webb typically points in what we call a pencil beam, like a very narrow point in the sky. So for our Hubble deep fields, and there are other standard astronomy fields, there's a goods field and a candles field and blah, blah, blah. For those fields, we have a lot of three-dimensional information. So it's like three-dimensional information in a pencil beam, and then there'll be a pencil beam at that field and a pencil beam at that field. To get all sky 3 dimensions requires a different type of telescope, a survey telescope, of which Hubble and Webb are not. But we are actually building a survey telescope right now in Chile called the Vera Rubin Observatory, which will image the entire southern sky. And then 3 days later, it'll image the entire southern sky. And 3 days later, the entire southern sky. And it's going to do that for 10 years. And that will build up that database that you're talking about, at least for the southern sky. Yeah.
Please tell us about what we could see with the much bigger JWST.
Yeah, the question is, you know, I said we need a bigger telescope to do like this question of, is there life on an Earth-like planet around a sun-like star? And can we answer that with statistical significance? If we're only looking at 5 planets, like JWST currently has the capability, and we don't find life on those 5, does that mean there's no life? No. So you have to look at a large enough number. And so in the most recent decadal survey, every 10 years, astronomers do a survey of their field. They ask, what's our state of knowledge and what do we want going forward? They identified this question of life elsewhere as a crucial question to answer. To do that, you need a telescope that is, you know, at least a James Webb diameter, if not twice the size, at visible wavelengths. So like a Hubble on steroids. That's what you need to answer that question. And just like I told you, JWST was designed to look at first light in the universe, but then I showed you galactic structure. I showed you star formation. I showed you an exploration of Jupiter. That 10 to 12 meter telescope that we want to build to do that exoplanet work will also take a whole new revolutionary leap for all of the other fields that we talk about in astronomy. And so in my own field, planetary science, imagine, if you will, images of Neptune like the Voyager spacecraft every day. That's what that 10-meter telescope would do for me. And someone who studies star formation will give you a different answer, but it's mind-boggling what it could do. And it's going to take us 20 years more to build. So we're not going to have that next year or the year after. Some young whippersnapper is going to have to do what I did on JWST and devote 20 years of their life to making sure it gets there. That's how we get these new telescopes. Somebody built Hubble, and I got to use it. Yes, sir, in the back.
how probative is the JWST capability of defining the map of the universe in terms of its edges and its center? I still am vexed by this idea that if the universe had a beginning at a single point and is expanded in all sides, and if we point from our solar system in any direction, we see deep fields of apparent galaxies moving away from us. Where is the center? Is there any trace of the umbilical cord and the navel of the universe?
Yeah. Yeah. So these cosmology questions are really hard, and we all need to drink a lot to really kind of get our heads around them. But I'm going to answer your question in 2 dimensions, and then I'm going to ask you to do the thought experiment of 3 dimensions. On the surface of a balloon, that is, it's blown up from the inside, or a soap bubble. That's maybe better than a balloon. Where is the center on the surface of a soap bubble? There isn't one, right? It's anywhere. So any point you pick, you can look, all right, around to a more distant point. All right, that's a 2-dimensional surface, but there's no center, right? And if the soap bubble gets bigger, then it takes longer to get from one point to another. And if it gets really big, you can't ever get from one side to the other, to the edge. Now that's 2 dimensions, but space is 3 dimensions, all right? I can't visualize this or explain it very well, which is why I am a planetary astronomer, right? So I study things you can send spacecraft to, I can understand it. But the same is true in 3 dimensions with space. There is not a center, right? It is all together. And so if we were on the other edge, further away, looking back, it isn't as if there's a brick wall that you get to. It's never ending. It's all one thing. And I'm sorry, I'm not Stephen Hawking, because he understands this stuff, but I don't. I can't give you a really good explanation.
So we want to go through the online questions.
We can come back though.
First online question is, does the JWST have fine enough angular resolution for limb viewing measurements of planetary atmospheres? This is followed up by a comment that says, limb views have a longer path through the atmosphere than do nadir views. So they are particularly sensitive to atmospheric composition and to clouds and aerosols.
Okay, so the comment is of course absolutely true about looking at the limbs of planets and having a longer optical path. JWST, I think that there may be tricky ways to get at what this person is asking by imagining when we have the transit starting, we're looking through the limb of the planet. And then as you go along, it's 2 endpoints and then it's the limb again. So I think we'll be able to pull out some information, but it's really challenging. But we have a lot of people who are very interested in that sort of thing. In terms of imaging exoplanets, I don't think we're going to have a lot of luck with that. I think we're going to have to be just super clever about how we use transits and about how we use the orbits of the stars, the orbits of the planets moving around the stars to map out different phase positions. So it's going to be hard.
Great, thank you.
Yeah.
All right, moving on to the next question. Let's see. Can you please comment on the selection of the orbit of L2 and why that particular orbit? And also the physics of the orbit is very interesting. Also, can you comment on how the orbit allows for the Webb always to be in position where the sun and Earth are shielded?
Okay, so the position of L2 was chosen because if you put a spacecraft there, it's you need to use very little fuel to keep it at that quasi-gravitationally stable point. L1 is super easy to understand, so let me use that first. L1 is a point between the sun and the Earth, and you can imagine if you draw a line between the sun and the Earth, there is some point where the gravity of Earth is balanced by the gravity of the sun, right? That's pretty easy to understand. You put a spacecraft there, it's going to stay there, right? L2 is on the other side, all right? So you have the gravity of the sun and the gravity of the earth. There's a point where they are about the same. And so that particular point is a place where it doesn't require as much fuel to keep it at that point, all right? If you put it out further away, you'd have competing gravitational forces. But out there, the gravitational forces are in a line, if you will. And we don't actually set it at the point. We put it in what's called a halo orbit around that point. And that, in fact, uses the least amount of fuel. So once you get in that orbit, roughly every 3 weeks, we need to do a little fuel trajectory maneuver to put it right back onto the orbit we want it to be. And why there? Why didn't we put it at L1? All right? Think about that, all right? Where the light from the earth would then be shining on the telescope. By putting it out at L2, the sun shield blocks the earth, the sun, and the earth's moon. It was designed to be large enough to block all three of those with that one sun shield. And so that's why we put it out there at L2. Was that the whole question?
That was the whole question. Thank you. And then we'll do one last question from online before we go back to our live questions. Let's see. It says, can you describe the effects of the micrometeorite strike that occurred into one mirror and how engineering plans assumed strikes over time?
Yeah. So once you put that big supergiant telescope and sun shield out there in outer space, nothing there to protect it from dust, micrometeorite strikes. So we did a lot of extensive studies. By we, I mean the NASA team, consulting with our ESA colleagues who currently have a spacecraft called Gaia out at L2. And so they have in situ knowledge of L2. We've had other spacecraft there as well, the MAP, WMAP and Planck, they were all there. So we knew a lot about the micrometeoroid environment, and we have models of what it would expected to be over the lifetime. And we designed JWST so by the end of our nominal 10-year mission, given the amount of micrometeorite strikes we expected over its lifetime, we could still have a fully functioning telescope. So we're out at L2, it's out there, we get a ping, we get another ping, we get another ping. Over the first, since we launched and put it there, by May, we had 4 different micrometeoroid strikes. But sometime in the end of May, we had a big micrometeoroid strike, big enough that it actually moved one of the mirrors out of alignment. And everyone's like, oh, well, the mirror's out of alignment. What happened? Oh, must have been a micrometeoroid strike. So when they brought the mirror back into alignment, we have a device on the spacecraft in the near-infrared camera called a pupil imaging lens. For those of you who have optics backgrounds, you know what that means. It means we can actually take a picture of the primary mirror, the pupil, and we actually took a picture of the mirror, and we could see in the mirror called C4 an actual ding, like there was a bump in the mirror where this thing had hit it and caused a strike. Fortunately, every mirror on JWST has a bunch of actuators on the back that allow us to change its shape, to move it. And so we were able to adjust the mirror that had been damaged to minimize the impact, no pun intended, from the micrometeorite. And because we had planned to have micrometeorite strikes, including of this size, we are still well within all the sensitivities as expected. People are like, well, wait a minute, this happened so soon after launch. That means your models are wrong. That's not how statistics work, people, right? We expected to have strikes of this size over our 10-year period. And we had one in the beginning, and that doesn't mean that our models are wrong. It just means we were unlucky enough to have a strike in the beginning of the period. If we get 17 more of those, then maybe we can talk about the model being wrong. So far, there have been no other strikes since then. Not even the small ones, I don't think. So, what? No, we're good. So we're good. We're not worried about the micrometeorites. All is well.
Okay, we go back to the live audience for questions.
Yes, sir.
Thank you. And that it's just an amazing presentation. You referenced a few times the 10-year nominal life. So what's the limiting factor? And is there any way to extend the life of the telescope?
Yeah, so if you had asked me that question on December 24th, the answer was we planned for a 5-year mission with the possibility of extension to 10 years, where the life limiting factor is the hydrazine fuel that we use to do station keeping and keeping us in the halo orbit. Because of our super exquisite Ariane 5 launch provided by ESA, we now have 10 more years. So what is the life limiting factor? We don't know what the life limiting factor is going to be. There are no other expendables on the spacecraft. There is micrometeoroids, as you heard. If our Kapton shields, our sun shield, get ripped, that would be bad. So that could be life limiting. As with any spacecraft, if you get a cosmic ray strike in the wrong part of your instrument, you know, and if you get if you get a cosmic ray, a high energy particle strike on a piece of the instrument, the ISIM control data and handling component, then you can't handle your data anymore. That's bad. So my guess, if I had to guess, is it's going to be some high energy particle that's going to hit an unfortunate bit of electronics, and that might do us in. But that might not happen for 20 years. Hubble right now was last serviced in 2009, and it has not been touched by human hands since then, and it is still performing absolutely fabulously. Occasionally we have safe modes where we're hit by some cosmic ray strike in a bad thing. We had one just last week. We don't talk about them simply because it's just like, it's a spacecraft. It goes into, those of you who work with spacecraft, they go into safe mode. You wait, you fix it, they come out of safe mode. So we don't talk about every safe mode we go into. So I can't really tell you. I'm kind of hoping it lasts for 20 years. I think that would be pretty cool. We don't have any other limiting factor right now. It's just the dangers of inherent in space.
Thanks for a fascinating talk. In your response to the first question, you talked a little bit about the accessibility of the data, and I'm wondering if you can talk a little bit more about that. So for example, does a group have to be at NASA to make some of the cool discoveries now? Is there expensive equipment that's required to do the analysis? And then second, just a few days ago, the White House came out with an announcement about open science that said that taxpayer-funded research would need to be made publicly available immediately. Will that impact your 12-month archiving?
Okay, so those are two really rich questions. In terms of who gets to use JWST or Hubble or any of our large telescopes, these telescopes are open to all. You do have to apply for time. Once a year, there is a call for proposals. And anybody who has a good idea and writes a scientific justification that is compelling, they have the opportunity to get time. How it's decided is every year the call goes out, and like there's a day, you know, I think it's December, so I can't remember the date right now. And you have to have your proposal in by that date, no exceptions, right? Then typically for Hubble or for Webb, we get about 1,000 proposals. We got, I think, 1,200 for the first year of JWST. Those proposals have to be written completely anonymously. You cannot say, my name is Heidi Hamill. I'm an amazing space observer. I know how to use telescopes. Let me use this telescope to look at Neptune. You can't do that. You say, you know, we have an idea to use JWST to look at Neptune, to do atmospheric dynamics. Certain models say this, you don't say who did them, or you can say, you know, models by Hamill et al., models by Smith et al. Say the other. It all has to be anonymous, right? And then they're all reviewed by teams of experts. There's an expert for galaxies, experts for solar system, experts for star formation, and they rank them in a triage. Like they read them all and they say, these are amazing, we will do. These, you don't need JWST to do them, throw them away. And then they argue over the ones in the middle. And typically it's 1 out of 10 gets time. It's very, very difficult to get time on all these telescopes. But that's how it's done. And by doing it in this anonymous fashion, there's no bias. There's like, you know, it doesn't matter who you are, where you are, what university you're at, what part of the world you're from. It's all open. So that's how you get time. And then that data all goes into the archives. Like I said, we have had typically a policy of proprietary time for 1 year, and then it is completely open. We're not sure how this new declaration is going to affect us, whether or not we need to make everything immediately available, or whether this 1 year protection for the people who came up with the idea will stand, because then it is fully open after that. So that's something we're still looking at. You, sir, in the back, yeah. Yeah, you. Oh, he needs a microphone.
We're a stone's throw away from the Capitol. I figured I'd the influence of Senator Barbara Mikulski. You referenced her a bit earlier. Can you speak to her influence in advocating for the telescope, and especially when it was at risk of cancellation in around 2013, I believe?
Yeah, Senator Mikulski, senator from Maryland. Maryland is where the Space Telescope Science Institute is. It's also where Goddard Space Flight Center is located. Senator Mikulski was a huge advocate for the Hubble Space Telescope and also for James Webb Space Telescope. And so there was a period in around 2010, 2011, where the House of Representatives said, enough of this JWST nonsense. We're canceling the program. And so we went into kind of a power mode. It's like, no, wait, no, it's really, you know, we'll examine it. And the reason, there's a very long, complicated story. Books are being written about how JWST came to be. We actually have a staff historian who attended all of our meetings over 20 years. When JWST was first proposed back in 2002, when I was first selected, it was called the Next Generation Space Telescope. And the team that proposed it made up a number for what the budget was. And it was absurd. I mean, it was ridiculous that everybody knew it. And, but nobody was, it was like the emperor has no clothes. Nobody was going to be the one to say the emperor has no clothes. You know, you can't build a 6.5 meters infrared cryogenically cooled space telescope. You can't do that for $400 million. That's nuts. And so we all knew that. But people bought into this mythos. And so eventually the budgets were not matching what was needed to build the telescope. And every year they needed money to build it, and they didn't have it because they had this ridiculously low budget. It was crazy. And so they said, we're going to cancel it. It's done. So we all said, no, please don't cancel it. You know, we will get it right. And Senator Mikulski commissioned a panel to evaluate it. And the ICRP, Independent Congressional Review Panel, was chaired by John Cassani, who was the chief engineer at the Jet Propulsion Laboratory, who did the Voyager program and the Cassini program. He chaired it, and they said, look, technologically, we have solved all the problems for JWST. Technology is not the limiting factor. The limiting factor is budgetary management. And it's going to cost you at that time, it's like $4 billion. They said, no, if you want to build this telescope right here, right now, 2011, you need to cost it at $6.5 billion, and you need to put this much money in the budget this year and this year and this year and this year, and then you can do it. And so what happened? Well, they did not put the right amount of money in the budget that year or that year or that year, and so that is why it ended up costing $8.8 billion, not 6.5, because if they had put the budget in at the time, but that's not the way Congress works. Sorry, daughter who works in Congress. They don't always listen to the scientists and the NASA people. You know, they have other constraints, and we can't give you the money you need in the year you need it. We only give you this much. And so that, I mean, I'm really super simplifying a very, very complex system. But It was not technology that limited us. It was how the budgets were managed, the years they were put in, how much reserve was in the budget in every year, how they spent the reserve in every year. All of that is a very complex interplay. And we learned a lot from JWST about truth telling. So we're talking about our 6.5 or 12 meter future space telescope. None of us are saying you're going to build it for $400 million, all right? We know that it's going to be probably a $10 billion or $12 billion if we put the funding profile the right way from the beginning, all right? We know that, all right? And so we're trying to be more upfront about that and handle the management of the costs appropriately. So we're trying to change the way we do the large mission management at NASA and our other agencies to be more appropriate and not to talk about the emperor having no clothes.
Thank you. So we're going to move on to some online questions. All right, so the next question is, if we can see almost back to the moment of the Big Bang, where has that light been in the meantime? If we sped straight away from the point of the Big Bang, the light from that event should have sped on past us and disappeared way beyond where we are now. Is the light traveling around and around inside the universe formed by the Big Bang, as opposed to going beyond and dissipating into someplace further out? And if it is circulating inside the universe, is it in effect being curved by the total mass of the universe to cause it to bend around inside the universe?
Oh my Lord. All right, remember the answer I gave you before? I mean, it's kind of the same thing you're asking. You know, we look in straight lines in our universe, but as I showed you and talked about with these massive galaxies, there are curves because space-time becomes curved by the mass of the massive clusters of galaxies. So things don't necessarily travel in straight lines, but we're not, I can't get into this issue of the curvature of the universe and whether things go around in circles and things like that. Apologies, I'm not the right scientist for that topic. So I'm just gonna punt.
No worries, no worries.
Classic MIT move, right?
Punt away. All right, so the next question is, why is the NGC nebula so well demarcated?
So you're referring to an image that I must have shown. I'm not sure which MGC nebula you were. Are we talking about the cliff's edge? Is that the one? I don't know which one they're referring to. Maybe they'll answer. NGC. Well, NGC stands for New Galactic Catalog, and it's followed by a number. And NGC number is a thing. So I don't know which thing we're talking about, with my apologies.
All right, so then we'll have to move on
Move
to the
on.
next one. All right, so what is the density of the gas clouds versus density of empty space?
Oh gosh, I don't have that number in my head, but I bet you can Google it. I mean, it must be a lot higher because we can see those clouds of gas, right? So it's a high enough density. I don't have, it's not rock, so it's not 3 centimeters per cubic centimeter. You know, I don't know the number. I don't know. But Google is your friend for details like that.
All right, last one from the online batch. Okay, are the exoplanet atmospheric absorption spectra redshifted, or are they too close, parentheses, local galaxy, for such an effect?
That's a good question. I like that one. The question was, are the exoplanet galaxies or the exoplanet spectra, are they redshifted as well? Everything is going to be redshifted, but those exoplanets are in our local neighborhood. So the redshifts are extraordinarily small, and we won't be able to measure them there. So in effect, no. You have to be looking at distant galaxies and even more distant galaxies to have a large enough redshift that you can see the shift. One reason the person, if someone who's been reading about exoplanets, they might ask that question because there's a different kind of technique we use to study exoplanets. We call the Doppler shift method. It's not the transit method, it's something different. It's where we look at the spectrum of a star and we look at its spectral lines and we can see them moving back and forth. And we know that there is a planet there that is pulling that star in its orbit forward and backwards. And so the spectral lines are shifting because of that motion, that Doppler shifting due to the presence of a planet. And we can use the shifting, red shifting and blue shifting of spectral lines to infer an exoplanet there. So there is an exoplanet technique that involves redshift and blue shift, but it's not the same as cosmological redshift and blue shift.
Okay, so we are officially beyond our end time, but since we're having such a good time, I'm going to go for 5 more minutes.
Yes, sir.
You're getting an awful lot of data from a long distance from Webb. I'm wondering about the data transmission problem. We've been told for years the limits on getting data from space, you just couldn't do it. Have you solved that problem? Did you do anything different? Or do you think the capacity for data transmission will ever be limiting?
Well, that's a pretty good question. So I'm going to break it up into 2 parts. The transmission limitation, I think, comes from the spacecraft to the Earth, right? And so this spacecraft is really close. It's only 1.5 million miles away. And so we don't even need a very big antenna to get back to Earth. So that's not a limitation for us. And also, this is not a big wide field telescope. And so even though we're taking lots of pictures, it's not really a big data rate in terms of today's capability. When we launched the Roman Space Telescope, which is a Hubble-sized telescope, but wide field, like 100 times Hubble, there's going to be that'll be a different question. But again, that's only going to be in low Earth orbit, so you just have a big enough antenna, not a problem. One of the interesting challenges, which is kind of associated with your question, is where do you pick up the data on the other side? We use something called the Deep Space Network, which is an array of very large radio telescopes all the way around the world. And the challenge with the DSN right now is that Mars Curiosity, Mars Perseverance, Voyager, and now Artemis, they all are using the DSN. And so we're actually running into DSN scheduling issues where, there's like, we need to look at JWST to download the data, or like, sorry, it's Artemis. But, just store it, you'll get it later. And, what are you going to say? Artemis is going to be human space flight. So of course they have to have priority. But, I think we worry more about that ground capacity than we do about our spacecraft. I mean, we send spacecraft to Pluto and beyond, and they don't need to have very big antennae on those spacecraft to get that data back to us. It's the ground station limitation that I worry more about than it is the spacecraft. Yes, sir, right here, this young fellow.
So the James Webb Space Telescope, I believe it operates on it only has a certain axis, certain field of view it can access because of its positioning at L2 and the way the field is split towards the sun and Earth.
Right.
So does that mean that effectively there are parts of space that we're not going to see because of its basically laser focus? As you mentioned, it's not wide angle, basically laser focused with a severe limitation on its area of view. So are there things that we're not going to see that we're then going to try and remedy with a different telescope or mission?
Yeah, the only thing we won't be able to see with Webb is the interior of our solar system. Because when we're looking out, we can't look directly out, but there's a sort of a donut shape around us that we can look at. And that donut shape then can go all the way from the North Pole to the South Pole, and then as the course of 1 year goes all the way around the sky. And so we can see everything in the sky with JWST. And there are places, the North Pole, where you can see it all the time. So we have a special program called, what's it called? I'm having a brainwave here. The North Ecliptic Field. The North Ecliptic Field, where we're going to be mapping out this sort of piece around the northern pole of the sky because we can view it all the time. So we're going to map that all out. But it's only the inside of the solar system that we can't see. Everything else, you just have to wait. If you miss it 1 year, like if Artemis says, sorry, you can't have the DSN, but what about Neptune? You got to wait till next year when it comes around again. So you have to be patient. And already for this first year, as the IDS, as an interdisciplinary scientist, I have guaranteed time on the telescope. I didn't have to apply. I did 20 years ago. All right, that's when I applied. You know, I have a whole program of, for me, solar system objects. And when we look out in the first year, some of the wind, because of the timing of where the planets are, we couldn't see them in the first year. Like, you know, they're just not visible. And so we have, they do allow us to go a little bit into the second year, but it's a long time after you've waited 20 years to be said, sorry, you missed your window. Got to wait till next year. But that's what you do. You just have to be patient. That's true of ground-based observing as well. I used the Keck telescope on Mauna Kea, and I typically, when I was really hardcore observer, I would get 2 nights a year. And if it was cloudy those 2 nights, sorry, Charlie, come back next year. So that's how it works.
Where are you on the Planet 9 controversy? And is Webb ever going to get involved in trying to take a look for it?
So the Planet 9 controversy, as you put it, is there are some astronomers who are looking very hard for an additional planet in the outer reaches of our solar system. There's a couple of different lines of evidence that suggest there may be an additional planet out there. And teams are looking. Mike Brown at Caltech, Batagan, there's a couple other folks. They're looking pretty hard, but you need a survey telescope to be looking, because you don't know where it is exactly. Even with all their different lines of evidence, they put you in a region. And so JWST is not a searching telescope. If they find Planet 9, they identify it, you can bet that JWST will look at it and characterize it and will do a really good job of it. But we are not a finding telescope. We're a characterizing telescope. Yes? I can't hear you. Stand up. Yeah, the question was, when we're looking at spectral lines and identifying them as specific elements, is there a possibility of finding a new element? Probably not finding a new element, because I think with our exploration here on the ground and filling out the periodic table, I think we found all the likely elements. But I will share with you that sometimes we see spectral lines that we cannot identify. And they're probably not elements. They're probably molecules. And so there are lines, PAH lines, PA lines, and that PA is a sort of shorthand for polycyclic aromatic hydrocarbon, which is a short way of saying a complex hydrocarbon, but we don't know exactly what it is. It's not formaldehyde, it's not acetylcholine, it's not anything that we've been able to identify, but there's a line there and it's something that's absorbing. So it's probably that we typically find them in dusty areas. So hence it's probably some kind of a carbon-bearing complex molecule with carbon and oxygen, maybe some nitrogen or sulfur mixed in, but in a pattern or a complex that we haven't been able to identify in our laboratories. That's part of the fun of being a spectroscopist, is when you find these lines, what are they? Let me share one anecdote. I don't know, some of the older folks here might remember when the comet Shoemaker-Levy 9 crashed into Jupiter, right? That I ran the Hubble Space Telescope program for that event. It sort of was my big, like, life-changing event. And one of my team members was really interested in spectroscopy. And so we did get spectra of the black impact sites that were left on the planet. And it was an absolutely gorgeous spectrum. It was like sort of really a pattern that was really very, and Roger Yell, he was on my team, he was sitting there. It's like, I know this spectrum. I've seen it somewhere. He had all these books he had brought from the library, these commentaries. He couldn't identify it, right? But he's like, I know it. I know I've seen this spectrum somewhere. And then at one point I heard, aha! I'm like, what? He said, I found it. It was pure sulfur. It was a pure sulfur spectrum, absolutely gorgeous. He showed it to him. I'm like, yep, that's it. You got it, buddy. So there must have some sulfur was dredged up and it was like in this moment, it was heated up and it was just like pure. So that's a spectroscopy. You know, these guys and gals, they love that stuff. Give them a line they can't identify. They're in heaven. That's right.
Okay, so I'm sorry, since we are 15 minutes over end time, I'm going to unfortunately have to end the event. I'm sorry that the kitchen is a little slow there are cookies coming out now. so you are welcome to stay. They are not going to kick us out, but we are going to end the event right now. And please take a look at the ICBH. ICDH module here brought by our past president, Vegan. And one other thing is you are going to receive by email a survey form for this event. And it's a feedback form for this event. Please fill it out if you can. Thank you. Thank you for coming today. Thank you.
Recording stopped.
Let me come down.